It's Monday, May 17th, 2021. This is for Physics CP, but I'm showing a periodic table. Whee! All right. I'm trying to explain what we understand about the universe. We began with the ancient Greeks in our astronomy unit and how they figured out that the Earth is bigger than the moon and smaller than the sun, and eventually up through uh, figuring out the size of the solar system, and then learning about stars and learning about the main sequence and giants and supergiants, neutron stars and black holes. Now I'm going to try to explain how the periodic table itself is a piece of evidence for trying to figure out the origin of the universe. I'd already described how Olber's paradox asks the question, why is it dark at night? Why is it dark? Why is the night sky dark? And the thinking was, if the universe were infinitely old and infinitely large, then every direction you look in space, there should be stars somewhere along that line of sight. So there should be no darkness. The entire universe should be glowing at the average temperature of the star. And it's dark. So we know the universe is not infinitely old and infinitely big. Now, what does the periodic table tell us about anything going on here? Well, there are some clues here. As we look out into the universe, we can see that by far the most abundant element in the universe is hydrogen, the lightest element of all. And that itself is a hint about how the universe was formed. And this number, I think the original value was something like about 75% of the original universe was hydrogen gas. The second most abundant element in the entire universe was helium at about 25%. And those two just about account for every bit of matter in the universe, right? 75 and 25 is 100%. None of this other stuff. The Big Bang theory accounts for this. So what do? First, we observe nature, and then we develop models and theories to explain what we see. And based on those models and theories, we make predictions. What would happen if we were to look for this? What would we see? What would happen if we were to test for that? What would we find out? And so theory and experiment go back and forth, hand in hand, over the history of science, trying to make better and better understanding of our entire universe. And as far as we can tell, there's no end to this game that we can play of trying to develop a deeper and deeper understanding of the universe. So it's an exciting field if you want to get into it. What we have observed is that most of the universe is hydrogen, and most of the rest of the universe is helium. You might remember that hydrogen by itself is basically one proton, and it's surrounded by one electron. The proton has a positive charge, the electron has a negative charge. This is a neutral atom. Hydrogen is one of those 7 diatomic elements that hate being by themselves. So what happens is 2 hydrogens will share an electron with each other, and that's why we always write hydrogen with a subscript 2 as a reminder that it's really, we can write it with the Lewis symbol like this. It's really two individual hydrogen atoms sharing a pair of electrons between them. Yep, that's diatomic. A bit about radioactivity. Allegedly, in your chemistry class, you learned about fusion. Fusion, as its name is trying to tell you, means joining I'll say elements, but you could say atoms, joining atoms together. So for example, in a fusion bomb, hydrogens go through a multi-step process, but in the end, in simple form, hydrogen ends up being fused together to create helium. Helium, no doubt you remember from the periodic table, is something that has 2 protons and 2 neutrons, and therefore it has 2 electrons when it's neutral. So we can begin with some hydrogens and go through some radioactive processes and fuse them together to create helium. We've seen in stars like our sun that helium can be fused together to create carbon. This was part of the story of Lives of Stars. And for stars like our sun, this is pretty much the end of the line. But if a star is more massive, then the carbon can go on to create, whatever the order was, oxygen, neon, silicon. And the more massive the star, the farther it can go up the periodic table until it gets to the element iron. Now, iron is element number 26 on the periodic table. And so what we're seeing is that through the process of fusion, it can take us up to iron, but not beyond. Yet there are all these elements beyond iron in the natural world and in man-made world. So what's the story with them? Iron is the end of the line for fusion. End of the line for fusion. When you took chemistry, not only did you allegedly study fusion, but you also allegedly studied fission. And fission, instead of joining atoms together, is breaking atoms apart. And one of the more common processes that you might remember is when you start with some element, I'll just put an X, and we call that the parent, and then it disintegrates into some daughter element and an alpha particle. Well, the alpha particle is just another name for a helium nucleus. Allegedly, in your chemistry course, you may have studied fission. And so fission is starting with elements that are high up on the periodic table, typically starting with plutonium, wherever that is. Here's uranium, here's plutonium, and the very first atomic bombs were fission bombs. The bigger more powerful advanced bombs were fusion bombs. So a hydrogen bomb is a fusion bomb, much more powerful than the original fission bombs dealing with substances, elements such as uranium and plutonium. These elements break apart. And as they break apart, their binding energy is released along with maybe gamma ray, well, other particles. And you can go down the periodic table by fission. So you can start with uranium and then go and become lead or polonium along the way, lead on your way down. These have different half-lives, different stabilities. The reason why there's so much lead is because of, its long half-life. And you can keep going down the periodic table, but iron, and I'm sure you remember that Fe is the symbol for iron. Iron is the end of the line for fission. It takes the most energy of all the elements on the periodic table to create a stable iron nucleus atom. And so by fusing together elements or by breaking apart elements, iron is the end of the line. And so now you should be kind of asking yourself the question, so how were these elements even formed? If we believe the universe began with just hydrogen, 75%, and helium, practically everything else, how'd we end up with uranium? How'd we end up with anything above iron? How'd we even get to iron? Okay, well, now in this current course, you've learned how to get to iron by fusion. So a star like Kronos in Lives of Stars basically fuses hydrogen to helium. It takes trillions of years, and then it just peters out from there. A star like our sun can fuse hydrogen to helium, and then helium into carbon, and then peter out. And then more massive stars can fuse to oxygen, more massive to neon, more massive up to when it hits iron, oh my goodness, fusion stops. When fusion stops, I kind of want to remind you that a star spent its whole life in a tug of war with gravity. That gravity is always trying to make it collapse. And as long as the star is shining, fusing, it's exploding outwards. And we have this, what they call it, hydrostatic equilibrium. Hydrostatic equilibrium, where they're in just a delicate balance. And as long as there's fuel, hydrogen at first, to keep the process going, the star is somewhat stable. Okay. It's when it becomes unstable that these interesting things can happen. All right, so what I'm going to do is flip over and go to Wikipedia, the most trusted source of information in the universe, and look at their fine periodic table under the category of nucleosynthesis. All right, so here we are over at Wikipedia, and they have a nice color-coded explanation chart of the periodic table. Color-coded. So let's go through this a little bit here. In this nice shade of blue, they are labeling all the elements on the periodic table that are believed to have begun when the universe was formed. And as you can see, I'm a little reluctant. Okay, As you can, yeah, you can see it fills the screen. Hydrogen and helium are the only two elements on this list. And when I mouse over, it says 100% Big Bang fusion. When I mouse over helium, it says 91% is from Big Bang fusion. But in the fine print, it says 5% of the helium that we see today came from exploding massive stars. So that's like when a supernova explosion takes place. And then it mentions 4% are from dying low mass stars. Okay. So this key here tells us our current best explanation, according to Wikipedia, which you know is not really reliable, in terms of accepted practice. This is the story that we're using to explain the periodic table. Okay, the top end is pretty easy to explain. So when you look at Americum, up to Lawrencium, these are man-made elements that we've been able to create in a laboratory. They're extremely short-lived, extremely unstable, and they're not found in nature. We don't really expect them to exist in nature. If they ever did, they disappeared essentially as soon as they were formed in nature. And the same thing is true when we create this in the laboratory. They don't stick around for very long. They disintegrate. And so here, interesting, technium number 43 is also man-made. Okay. It says here that an element such as lithium, when I mouse over it, interestingly enough, it says 23% of it, of what exists today, came from the Big Bang. So that is like the heaviest element ever created as the universe began. And everything else had to evolve, starting off with just hydrogen, helium, and a sprinkling of lithium. And in fact, it just shows up as a little bit of blue. That color represents 23%. So I guess there's 100 grids here. 13% of this comes from something we haven't talked about. 64% of lithium comes from something we haven't talked about. So let's start talking about it. When a low mass star dies, the element shown in green can be created. This is news to me. When I was in college taking an astronomy course, basically, as I understood it back then, the exploding supermassive stars created the heavier elements. Notice that they go above iron. And the explanation is, during a supernova explosion, the temperature and the pressure become so great. So gravity is trying to crush the star, and the temperature and the pressure skyrocket so much that during the moment that the star is exploding as a supernova is when it has so much extra energy that it can sink it into building elements higher in atomic mass than iron. And so all this yellow here, for example, the element gallium, the only source of gallium is in a supernova explosion. And I'm mousing over oxygen, by the way. The only known source of oxygen is in a supernova explosion. The air that you are breathing right now was formed during the death of a star. Let's see, you're made mostly of carbon. 25% of the carbon in the universe was formed as a star exploded. And it says here the other 75% came from low mass stars that were dying. Now we'll have to look into that a little bit more. But when someone says, oh, you are star stuff, they mean it literally. The elements on the periodic table from which from which all known life has evolved was created by a star dying somewhere out there near us in the galaxy. So all the yellow that you see here. Now, what are humans made out of? Carbon, nitrogen, oxygen, hydrogen, phosphorus. Those are the main ingredients of humans. And there's no way you can have life on Earth unless a star had died in the past. There's a theory that there could be life based on the element silicon instead of the element carbon. Well, same thing is true about silicon. That element is only created when stars die. So that's food for thought for you. Okay, so what else do they say here? They talk about cosmic ray fission. I've never studied it. Merging neutron stars. I've never studied it. Exploding white dwarfs. I didn't even know a white dwarf could explode. And yet that accounts for 42% of sulfur in our universe and 44% of argon in our universe. And by the way, when you look at helium today, the helium that we are enjoying in your party balloons is not the helium formed during the Big Bang. Just to be clear, all that helium has already left the Earth. The helium that you are enjoying today are the alpha particles being emitted by radioactive decay in the core of the planet. And as it seeps out of the ground, we find these pockets of it here and there, and we collect it and sell it to you as party balloons. Okay, so you're not using primordial helium in your party balloons. Sorry. Now I'm going to back up to this Wikipedia article before this slide and see what they have to say about these other sources. Oh, nice. And back up one more slide. The history, this whole thing is called nucleosynthesis. So the theory about how the periodic table was created, how it was built. Okay? And here's the abundances in the universe on a log scale, right? So really, nearly everything is hydrogen. Nearly everything after that is helium. Iron is starting to stick out because once you get the iron, you can't change it to anything else. This is what you would study in a college course that says, oh, okay, so a neutron can become a proton and an electron. This is electron emission, right? And it gives off a little neutrino of energy, well, a little neutrino. Here is stuff way a little bit beyond what you probably had in your chemistry course. Let's get down to the little details. So they're claiming when neutron stars collide with each other, then you can get some of these elements created. They're claiming that cosmic rays can cause some of these elements to be created. What I wanted to see was about exploding white dwarfs. I don't see anything here that convinces me that that white dwarfs explode. Okay, so I am going to try to do a pause to the video Actually, I might not even be recording the video. Yes, I am. Okay, I believe I'm now recording this. So I did a Google thing, exploding white dwarfs, because I've never heard of it. And here's what Lord Google says. Let's scroll down to this one. What causes a white dwarf star to explode as a supernova? And the best answer from 3 days ago from physicsworld.com is a new explanation for how white dwarf stars explode as type 1a supernova has been proposed by astrophysicists in Brazil and Mexico. Their models suggest that the explosions are ignited when primordial black holes collide with white dwarfs. Okay, well, I can go along with that. I don't like the idea that a white dwarf star, based on everything we've studied this unit, on its own would explode. But I can certainly believe that when a black hole runs into something, that an explosion is going to take place. Black holes will attract all matter that they encounter so violently that they would be glowing X-rays as they fall into a black hole. All right, we're on our 3-minute break. Let's go enjoy that right now.